In this video, I want to take a look at the algebra of polynomial functions that you might have learned in a pre-calc class, but then again, you might have forgotten it because you haven't used it very much yet. So the reason that I want to do this is because in solving nth order homogeneous differential equations, we're going to be solving polynomial equations. So I want to get some idea about what's going on with polynomial equations. First of all, I want to remind you that factors of polynomial are in one-to-one correspondence with zeros or roots of the polynomial, right? A zero or a root is an input value, so a value for your independent variable, that makes the output variable be zero. Right? So you can think of it as an x-intercept, right? And the thing is, if you have a factor of the polynomial, a linear factor of the polynomial, like x minus a, then x equals a will be a spot where the function is equal to 0. Likewise, if x equals a is a place where the function is equal to 0, then x minus a will be a factor. Okay. These functions that I keep saying are polynomials. I'm only talking about polynomial functions at the moment. Okay. Now, the fundamental theorem of algebra. This was proven by Carl Gauss in his PhD thesis. And it does not say, but is essentially equivalent to, every nth degree polynomial has n linear factors if we allow for complex coefficients. Actually, what Gauss proved was that every nth degree polynomial has one linear factor. And of course, the other one would be an n minus first degree polynomial, which we can argue, well, hey, well, that would have a linear factor. And then you can just keep factoring out linear factors and you'd end up with a total of n of them. So the net result is that every nth degree polynomial has n linear factors. But in order to get that, you have to allow for complex coefficients. X squared plus 1 does not factor over the reals, but it does factor over the complex numbers. That would be x plus I and x minus I as the two factors. Now, there's another theorem, which is not the fundamental theorem of calculus, but it's still pretty useful from the point of view of what we're going to be working with. And that is this. If I don't allow complex numbers, so I have polynomials with real coefficients, I know that I can always factor it into linear and quadratic factors. I never get stuck with an unfactorable cubic or an unfactorable fourth degree, that they always factor into at least quadratics, if not linear. Now, this is not immediately obvious. Actually, with the odd degree polynomials, I think it is obvious, because an odd degree polynomial heads up to infinity on one side and down to minus infinity on the other side. So it's got to cross through the x-axis somewhere, and if it crosses through the x-axis, that's a 0. That means that you have a factor, right? So that would be a linear factor where you had that intercept. But the even degree polynomials, it's not as obvious. For instance, here's the graph of y equals x squared plus 1, sorry, x to the fourth plus 1, which clearly does not cross the y-axis, right? The lowest it gets, sorry, it doesn't cross the x-axis. The lowest it gets is 1, and goes up from there. So there's not an obvious linear factor here. However, I can factor it into two quadratic polynomials, like this, x squared plus radical 2x plus 1 times x squared minus radical 2x plus 1. And you can verify that this is correct by multiplying it out. It's a big FOIL, right? So you get the x squared times x squared, that's your x to the fourth. The x cubes come from x squared times that, and that times x squared, but notice one of them is minus radical 2x cubed, and the other is plus radical 2x cubed. They go away, because there's 0 of them over here. The x squareds come from 3 places. You've got this x squared times that 1, and you've got this x squared times that 1, and then you've got the radical 2x times the minus radical 2x, for a grand total of 1 plus 1 minus 2. 0 x squareds. Likewise, for the x's, they come from this radical 2x times 1, and that 1 times the minus radical 2x, canceling out again. There's no x's, and then you get the 1 times 1 is plus 1. And so sure enough that this does factor as that, as those two quadratics. Now, I'm positive that they do not factor any further, because if they did factor further, I'd have linear factors, which means I'd have x-intercepts, and I know I don't have x-intercepts. So this is as far as it's going to go. Now notice that this didn't factor into integer coefficients, right? That I had to, not even rational coefficients. I needed to use radical 2's in here, some irrational numbers as my coefficients, but they're still real. I didn't have to go to imaginaries here. Okay. Now, the thing that's really useful about this for us is that it tells me that when I'm trying to find solutions to differential equations, and I'm ending up having to find solutions to polynomial equations, that those solutions are all going to come in only two ways. They're going to come from the linear factors equaling 0, which means the solutions will be real, and they come in complex conjugate pairs, because when you got a quadratic like this, when does that equal 0? Well, you can use the quadratic formula. Negative b plus or minus squared b squared minus 4ac all over 2a, and if b squared minus 4ac is negative, then you get that plus or minus that same imaginary part, and so you get complex conjugate roots. And I know what to do with reals and complex conjugate solutions to these polynomial equations when I'm solving my differential equations. Okay, so that's what we'll do next. Well, maybe not next, but soon we will actually start solving some differential equations. But I just thought we really should refresh this algebra from your past.